with that, I'd like to welcome you all to the May edition of the BLT seminar. We're lucky to have our first European of the season, Emanuele Delucchi, combinatorial invariants of finite metric spaces in the Wasserstein arrangement.
Well, thank you very much, of course, for the invitation, for the nowadays renowned BLT seminar, I should say. And thanks everybody for joining, from all places all around. So I'm going to give this kind of online talk, and there are many words in the title. So let me just start to see what I am going to say. So it's combinatorics, there are some finite metric spaces, and of course, an arrangement of hyperplanes. And so the way I got in touch with this circle of topics is via some short paper by Vershik, who proposed the following kind of problem. He says, well, there is actually a canonical correspondence between metric spaces and polytopes, right? And somehow then the question arises, can you classify metric spaces in terms of these polytopes? Okay, so there must be some way that Vershik will tell us, right, that for every finite metric space, I construct a polytope, and I want to see how the polytope changes if the metric space changes. Okay, so the problem of classification, I would say it's still a problem. So this is a talk more about a problem than about a solution. But in the short time and with this online medium, I would like at least to tell you, what kind of polytopes are we talking about? Okay, maybe we'll see some examples to get a feel for these things. Maybe then I'll give some contexts of where this comes from. Okay, how did Vershik come to this? And then I'll tell you a little bit about the classification problem and what we know, especially what we don't know, so that maybe you can lend a hand. Okay, so without further ado, one preliminary slide. So I'm going to talk about metric spaces, right? So this should be kind of a quite known thing. So metric space is some set. The distance function is symmetric. It should satisfy the triangle inequality. If I go directly, I am not going farther than going through a third point. And I want non-degenerate metrics. So distance 0 only happens for identical objects. Of course, in our case, we will be today mostly concerned with the case of finite sets, so metrics on finite sets. And just a little example or notation that I will use to tell you about some metrics. So there are several ways to communicate a metric, maybe the list of all the values, but for the purpose of effective graphical communication, I usually will use this kind of examples. So I will draw some graphs, edges and vertices, with some weights on the edges. And maybe the little twist is the following. So given a graph with weights on the edges, I will select a subset of the vertices, okay? And the subset is the, full black set of vertices. And I'll say, well, my graph with the given weights will define a metric on my set of black vertices. And how does it do it? Well, I look at two black vertices and I ask myself, what's the lightest path that connects these two vertices? So for the case of V and W, there is a path of weight 5, there is a path of weight 3, so the distance is 3. I mean, this is kind of a simple thing. Just, I will display some graphs with some black vertices. So I will mean the metric space induced on the black vertices by the associated labeled graph. Okay, so that's a metric. And now I have already told almost 5 minutes. I have not yet told you what my polytopes are. Well, they're not mine, but the polytopes that Vershik tells us to look at. Okay, let me give a definition, okay? And then immediately some examples. So I start with a finite metric space, okay? And so my polytope will live inside this Euclidean space, by which I mean it's a Euclidean space and one coordinate for every element of the finite set, okay? So the standard basis vectors, let's say, of this are just such little vectors, right? Ex, where x is an element of my metric space. And if I have two distinct elements of my metric space, I have two distinct standard basis vectors that I can subtract one from the other. Okay, I have not yet told you anything about the metric. Where does the metric enter? The metric is here. I divide this vector, okay, by the value of the metric. That's not zero because x and y are distinct. And of this set of points, I take the convex hull. Okay, so that's a convex polytope inside r to the x. Okay. Okay, before I give some example, this polytope appears with different names in the literature. Sometimes it's called Kantorovich and Rubinstein polytope. Sometimes it's also called a Wasserstein polytope. And in true Swiss compromise fashion, I will just call it with all possible names. So this is the Kantorovich-Rubinstein-Wasserstein polytope, KRW, okay? Okay, that's, I mean, we already see that the whole thing lives inside the subspace of all vectors where the sum of the coordinates is zero, right? Because the sum of the coordinates of these are always zero. And in fact, this is a full dimensional inside here. So this thing, the dimension is catenite of x minus 1. Okay, how does it look like? Well, let's look at some examples. Here on the bottom, I have some examples for the very easy case where my metric space has 3 elements. Okay, so let's say I have some metric space. Let me draw it as a graph like this. And maybe all distances are 1. So it's a metric space where every pair of points is distance 1. Now, of course, all these denominators are 1. And so these points here, which for brevity, I will just call Pxy. Okay, in this case, xy is Vw, Wz, Vz. So now these denominators are 1. And so these points are just differences of standard basis vectors. I mean, we know this is a root system of type A2, right? So exactly here, you see. So, and now I just take the convex hull of this thing, right? So in this case, my polytope is a hexagon, a regular hexagon, okay? No big deal, okay? Okay. Now, what happens if I change a little bit my my metric space? Let's say I make these points a little bit farther away. Okay, V and W are now a bit farther away. So it means that the point where V and W happens, this vector gets shorter, right? It gets a little bit shorter, let's say here. Okay. So what's the convex hull? Well, it's actually still a hexagon. Okay. So combinatorially, it's the same polytope. So what I mean by combinatorial structure, well, not really anything having to do with metric, but just, same type and incidence of phases, right? Okay, so you see, I made these guys a little bit farther away, so I pushed these vertices in. It's always a hexagon, okay, but it kind of changed. Now, the critical case happens if I take V and W even always more apart. So the critical case happens when I have a situation like this, right? Where, let's say, this is of length 2, right? So in this case, V and W is divided by 2. So I am at the half of these vectors. And now my polytope is a rectangle. okay? You see, now it changed the combinatorial structure. It has only 4 vertices, 4 sides, okay? So somehow I can deform my metric space, the polytope deforms, but doesn't change the combinatorics, right? At some point, my polytope changes combinatorial type. Okay, so and the problem or the question is, how can I understand what's the combinatorial type of the polytope if I know the metric space? Before I go further, let me just, in case somebody has heard about this, one can also consider the polar dual of this. And the polar dual of such a polytope is, well, it's full dimensional inside B. So the polar dual lives in B. So the polar dual is all the elements in B, such that the difference of coordinates is at most the distance. Okay? So if you think of an element here as a function from x to r, right? This amounts to say my function v is Lipschitz with Lipschitz constant 1. That's one of the reasons why this is called the Lipschitz polytope. And I don't want to dwell too much on it, but for people who like polytopes, you will know that polar dual basically carries the same combinatorial information as the original polytope. So to know about, phases, numbers, and incidence of this is basically amounts knowing incidence and type of phases here. So we could study either of these. I will focus today only about this, but you might be interested also in this other guy. For example, these Lipschitz things are always alcoved. They are also tropically convex. I mean, you might have reasons to study those. Okay, so that's the definition and a little example. So please stop me if I am too slow, too fast, too trivial, or whatever, or ask questions. So I feel I should give you a little bit more of an example than this 3 points. I mean, hexagons and rectangles. I'm hopefully not giving a talk on hexagons and rectangles. So here is maybe some example with 4 points. And remember my convention, right? What do I mean? That's, my convention is that if I don't write anything, the weight on the edges is 1 everywhere. Okay? So this is a metric space with 4 points. Any 2 of these have distance 2. Okay? So up to scaling, you understand? So now all the differences of standard basis vector have the same denominator. So up to scaling, I'm again a root system, this time of type A3. So this polytope is really the root polytope type A3. And now you see all root polytopes are special cases of these Kantorovich-Rubinstein Wasserstein things. Okay. Now, of course, here I can modify my metric space. For example, I take this and I split. So now this is a metric space on 4 points. Some of them have distance 3. Some of them have distance 2. Okay. And somehow passing from here to here, I don't know if you see it very well, this guy had some quadrangular face that now is broken up into 2 triangles. Okay? These things happen. Okay? And you see, as I go around, I don't want to comment too much. I go around here, I get different polytopes. You will notice from the slide before, this guy that I'm circling, these are 3 points, all equidistant to each other. Remember, this was a hexagon. See the hexagon, right? So I have now attached one more antenna, and what happened, I did a double pyramid on this hexagon. So this stuff happens. It's not completely random. It's also not completely clear what happens. To be completely honest, in this particular case of this slide, notice that all of my metrics I can represent with a graph that is a tree. Right? All of these graphs are trees. And every metric that I can represent in this graph way on a tree is called a tree matrix. And in this case, if I have a metric which is a tree metric, somehow the tree is uniquely determined. It is kind of a canonical way to represent the metric. Okay, for tree metrics, we have actually a more classical canonical way to represent, namely via this tree. Of course, the fun starts when I have not trees, right? So again, I don't want to go over everybody, but here I have some kind of graphs. They are not trees, right? And you see the polytopes can be quite easy, just a box, right? And then I can modify my metric space, and now one of the sides of the box breaks up into two triangles, right? That seems to be kind of a move, breaking up into two triangles. And for later on in the talk, I want to just say I could represent these metric spaces in many different ways. For example, I could choose the complete graph on 4 vertices, right? And just say distance 1, 1, 1, 1, 2, and 2. You see? This would represent the same metric space. So why did I not do this throughout? And why do I exactly choose to write this? Because these graphs, these are a classical thing, which once again, I will not go into if not, forced to, but so these are also canonical ways to write down finite metric spaces. These are what calls tight spans or injective hulls. Okay, so every finite metric space has, since the 60s, with work of Isbell, some canonical polyhedral complex attached to it. That's called the injective hull and the tight span. This was then rediscovered in the 80s by Dress and so on. But this is somehow something that people have studied a lot over the last 30, 40 years, right? So that's a known invariant of finite metric spaces. And here we see, and then I will end it with examples. I want to look at these 2 examples here, okay? So here I'm deviating by from my convention. So on the left-hand side, you see, remember all the weights are 1, okay? On the right-hand side, you see I wrote this a little bit longer. Let's say, right, the horizontal edges have length 2. So the gist is these tight spans, they are combinatorially equivalent, right? It's 1 quadrangle with 4 antennas, okay? But the polytopes are not combinatorially equivalent. For example, this guy has a square face, and the guy on the right is simplicial. Okay, so this suggests that these polytopes, so if I classify metric spaces by way of the combinatorial type of these polytopes, I get kind of a finer invariant than the classical tight span. At least from this example, it would suggest this. We'll see it's a little bit more complicated, okay? But the upshot here is the polytopes are some, let's say, new or less studied objects associated to metric spaces. There are some classical things, tight spans, that many people have studied, right? And maybe we can compare this as invariants to try to understand, okay? So I will end it here with examples. And before explaining to you what we know at the moment, I promised that I would give a little bit of context. I mean, why did people come up with these polytopes, right? Where does it come from? Has it been used or looked at all? So the context, and this is of course a most dangerous slide because I'm not an expert in this in any way, shape, or form. Okay, but to give an idea. I mean, if you hear words, names like Kantorovich and Wasserstein, this must have to do with transportation problem some way or another, okay? So the transportation problem, we could phrase it as follows. So I have 2 given, let's say these are distributions, okay, on the same space X. So I want to find a transportation plan, which is actually some psi on the product here, which agrees with the given ones on the margins and minimizes the total transportation cost. Okay, the distance here is the unit transportation cost. Anyway, whatever. To find to prove that this infinite exists and to find it is transposition problem. So this exists, and this defines some measure of the similarity of these two distributions, right? So given two, let's say, distributions, I can say, they are far apart or close together according to whether the transportation problem, has an advantageous or less advantageous solution. And using this, you can define a norm on our good old codimension one subspace of some zero of coordinates by selecting for every one of these sigmas, right? You select the positive and the negative part, you run the transportation problem, blah, blah, blah. And this gives you, in fact, a norm. This norm is a polyhedral norm, and the unit ball of this norm is our polytope, okay? So I will, only under duress, I will try to say something more than this about this context. But just to say, so this comes from the transportation problem, and the polytope we are looking at is the unit ball of some polyhedral norm, okay, that arises in this context. Now, on a more serious note, so I found, so there is a survey paper by Vershik. The paper is called, I think, Long Story of the Kantorovich Transportation Problem, which I think, at least for my understanding, is a good, non very technical introduction, and this helped me get in touch with this context. That's for the, okay. But that's not my main point of interest, actually. Some of the motivation, I mean, first of all, the problem exists, and so we have to study it, right? But people have looked at these things quite recently, in fact. There is a whole story related to algebraic statistics. There's this recent Oberwolfach book called Metric Algebraic Geometry by Brading, Kohn, and Sturmfels, where one chapter is dedicated to these KRW polytopes and some of the application, particular in algebraic statistics. There is some other work on, the kind of statements here, let me put it like this. The kind of statements are, if you know the number of faces of your polytope, or if you even know the actual faces of your polytope, this allows you to run some algorithm or to bound the complexity or runtime of some algorithm on some of these computational problems, okay? So knowing the faces, or at least counting the faces, is a people have looked at this. Also, my last context that I want to mention is in some kind of mathematical phylogenetics. The idea is that you look at evolution data, and we usually think, evolution builds a tree. So my graph would be a tree, and maybe with long and short edges, except depending on whether mutation happens rarely or frequently. So the actual applied people, their genomic data are not only trees, they are more complicated metric spaces, okay? And so the problem arises there to kind of handle these more complicated kinds of metric spaces. And for their algebraic statistic, they want the space of these metrics to be nicely stratified. So maybe these polytopes give a nice stratification of this space of metrics, okay? But, let's return to our core problem, right? The main problem here, which may be then useful for some other things, is, okay, let me look at the space of all metrics and see how it is subdivided by the combinatorial type of these polytopes, okay? So we'll be looking for the next 20 minutes at the so-called metric cone, okay? So what's the metric cone? So the idea is that a metric is really defined by its values on every pair of points, right? So a metric is a point in R to the x choose 2. So it's a vector whose components are, it has one component for every pair of points. So of course, not every assignment of numbers to pair of points is a metric, right? The symmetry is guaranteed that I'm looking at unordered pairs. Of course, triangle inequality should be satisfied, okay? And this should be all strictly positive. So this is, of course, a cone, okay? It's a half-open cone. which I will draw in the next slides. So actually, I will just write m little n if my metric space is just the set of, the elements are just the numbers 1 through n. That's, practical. So, okay. Good. So definition of the polytopes we have seen, let's say, the hexagon and rectangle for 3 points, for 4 points, a little bit more complicated. Okay. Some people have looked at this, and our main question asked by Vershik is, okay, this is the space of all metrics. How is it subdivided by the polytopes? Okay, if I fix a polytope, what's the set of metrics that has this polytope? Okay, one of Vershik's suggestion is that this might be some kind of a universality statement like Nyof, right? So depending on the polytope, this set can be arbitrarily wild. Okay, the answer is no, actually. So, and I'll explain. So let's return to our 3-point case, just to tell you the picture I actually have in mind when I think of metric cone, right? So a 3-point metric is a point in this Euclidean space. I have to specify 3 numbers, okay? Of course, this can't be 0. So the metric cone is a cone that is pointed at the origin. And what I'm drawing is a slice of this cone, okay? It's a triangle. It's defined. So the 3 possible triangle inequalities define this supporting planes. And of course, this, you see, it's not closed because it can't touch this coordinate plane because this point has distance of u and w equal to 0, and I don't want it. Okay, so it's kind of a half open, half closed thing. So, oops. Now, if for every point I write down this tight span, so for 3 points, these tight spans are trees always. Okay, so you see at the very center, I have this kind of metric spaces, right? 3-legged trees with 3 equally long legs. As I approach the boundary, one of the legs shrinks. And if I am on the boundary, my tight span is just the line graph. Okay, so as far as the shape of the tight span is concerned, I have one big region where the shape is always the same, right? And then I have 3 boundary pieces, right, where it has a different shape. Okay, so our polytopes, you remember, the polytope is either a hexagon or a rectangle. Okay, and in fact, it's an hexagon always in the interior, and it's a rectangle exactly on the boundary. So for 3 elements, we don't, looking at the polytope is equivalent to looking at the tight span. Okay. So now it gets a little bit interesting. 4 elements. So 4 elements. So first of all, look at these guys, right? Of course, depending on the length of these edges, this defines a class of metric spaces which is 4 parameter. And if I quotient out by all of this set of, this is a linear subset, right? I quotient out this 6-dimensional metric cone, I am left with a 2-dimensional picture, okay? And I can't draw the boundary because it's complicated, so let's look at the interior. So in the interior of the metric cone on 4 elements, I have this guy here, which represents this kind of metric spaces. And then I have 3 rays, which represent this kind of tree-like spaces. Okay? And for those who are familiar with the space of phylogenetic trees by Bilera, Holmes, and Vogtman, it does have this shape, right? So we are on to something. Of course, we have these non-tree guys, right? So here I have a region with this, here I have a region with that, and here I have a region with that. They only differ by the labeling of the points, basically, okay? So classified in terms of tight spans, these canonical, injective hulls of metric spaces, this has 3 big chambers, let's say, okay? And the 3 rays that separate them. Now remember my previous slide. we know that really there are two types of these guys, right? If I stretch the horizontal edges, I get different polytopes. So let's look at the polytope picture. So the polytope picture subdivides this big region, right? Because we know there are different polytopes for the same tight span. So now I have here 6 regions for these simplicial polytopes, okay? And the picture is a little bit, then I have one additional array for this almost simplicial, let's say, polytope, right? And so now my stratification is a little bit like that, okay? Although this and this have different meanings, so to speak, right? But the stratification is really 3 lines meeting in a point. And hyperplane people tend to like these things. So what this picture is telling me is that in this case, with 4 points, the subdivision of metric spaces according to the type of the polytope is realized by some kind of a hyperplane arrangement, and it is finer than the classification in terms of tight spans, right? Because this is a coarse fan, and this is a finer fan, okay? Okay, now I should
Yeah.
give, yes, Josephine, yes,
Can I ask you a
please.
question? Yeah, I'm a little confused about the linearity space because if you go back to the three-point thing when the size is 3, right? You have like different, yeah, that's right. You have different trees, but they have not everything is in the linearity space. But why is it that for the 4-leaf one, everything is in the linearity space? You see what I mean? Here you make a difference
Yes.
between like the trees that are aligned on
Yes,
the line.
absolutely. So the linear space is because I have to draw this. So
Okay, it's your choice for drawing it. It's like linearity space can be further refined into
absolutely. Yes, yes,
okay,
yes,
okay.
yes, yes, yes. Yes,
Right.
thank you.
Okay. I see, because it's a cone. Well, it's
It's
not the
cool.
linearity space of a cone, is it?
No, it's the linear space of this arrangement,
Of your
actually.
picture. Okay, of your arrangement. I got it. Yeah, all right.
So I'll thank you. Yes, of course you.
All right, thanks.
Yes. As Josephine's question demonstrate, I should tell you something. At this point, one can't take any more examples. One would like a statement. So here is the statement. Okay. So my metric cone can be subdivided in different ways. Okay. So either according to tight span, okay, and that's a well-known thing. I would say, I would dare to use the word classical for this, right? It's studied, it's related to the regular triangulations of the second hypersimplex. And then we have this kind of, I want to say, new thing, right? So first of all, it is a fan. So the strata are always cones, nothing wild happens, okay? And it corresponds to the secondary fan of the root polytope of type A, okay? Okay. And our suggestion is to look at some arrangement of hyperplanes which can allow us to study the situation. So let me just give you the definition of this arrangement and then discuss the relationship. So this arrangement is, of course, in the same space where the metric cone lives, okay? And now I'm going to interpret this, of course, as, every coordinate is an edge of the complete graph, Kn. And now the construction is as follows. So for every even cycle of this complete graph, so for, let's say, an even cycle, it's a cycle, and it's even. So even means I can say this is A1, B1, A2, B2, and so on, up to AB, AB, BK, okay? For each even cycle, I define a hyperplane, which consists of all the points in here, okay, such that the sum of the coordinates corresponding to, for example, the pairs AB, so that's coordinate AIBI, is equal to the sum of the other edges, sorry, red, the other edges, okay? So, and these are the edges represented by X AI BI minus 1, okay? So anyway, for every even cycle, there is such a hyperplane, okay? And then our Wasserstein arrangement is the set of all these hyperplanes where C is an even cycle of Kn, okay? So there are three fans, okay? There is this, I want to say classical, okay? So there is this, which for the moment we know it's a fan, not clear how it's, you know, how it looks like. And then this, which is the fan induced by this arrangement of hyperplanes, okay? So here, so in the previous slide, this arrangement is exactly these three lines meeting in a point, okay? And it coincides with this, okay? In general, there is a slightly unfortunate news or fortunate, depending on your taste. So in general, these three things have the following relationships. So this arrangement is always a refinement of this of the KRW polytope fan, okay? So the arrangement thing is a strict refinement of the polytope fan. And in fact, they are equal for n smaller or equal than 5. So the steps happens at 6, and we'll see afterwards, okay? And how are these related with the tight span things? So in fact, neither of these are either a refinement or a coarsening. So not, so neither coarser nor finer. Okay, so somehow there are two worlds that don't talk to each other, okay? uh, so this Wasserstein world seems to be, so actually neither coarser nor finer for n at least 5, okay? So in the 4-element case, everything seemed fine. But on 5 elements, okay, I have two metric spaces with different tight spans and equivalent polytope. You don't believe me? Here they are. Of course, everybody sees immediately by eye, right? So I'm sorry, of course. But just to, I mean, for the people who, so these are two different tight spans. You see here only quadrangle and here an hexagon, for example. Just this tells you they are not combinatorial. But both polytopes, if you compute them, they are combinatorially isomorphic. They are 4-dimensional, and here is a Schlegel diagram, okay? Okay, this is just to say, I mean, these things are proved by, you know, find an example, find an example, compute an example. Okay, so in my last, so let's take stock for a moment. So now we have kind of started to address this, how is the metric cone subdivided by these polytopes, okay? So at least no kind of universality thing goes on. It's a fan. It's really the secondary fan of the AN root polytope, okay? It is refined by some arrangement, which is not so bad. I gave you this, I mean, it's not so bad, but honestly, I have never seen this kind of arrangement before. So if anybody has, and, you know, these are related by refinement, and somehow the thing is neither coarser nor finer than the subdivision by tight spans. Okay, so the thing I have not yet addressed, and I want to do it in my last 5 minutes, is okay, parameter spaces, subdivision, but if I give you a metric, can you, you give me a metric, can I tell you the polytope? One example, okay? How can I compute these things one by one? Well, that's not easy, of course, either. So there are some general results by Gordon and Petrov that characterize somehow the faces of one specific polytope. And I'm only going to show this because, of course, this is related to the hyperplanes we use for this arrangement. But the only kind of explicit results that I know, they are for the metric spaces that are trees. And in this case, we have, first of all, these dual guys are zonotopes. And we can count the faces, we can express the F vector of the KRW polytopes of trees by counting some subgraphs. Counting these subgraphs may be easy or difficult depending on your tree, but there is a, let's say, a closed thing. Okay. Furthermore, as a further special case, for the metrics that I can represent on graphs where all the vertices are black, so to speak, right? So the polytopes you get in those cases are so-called symmetric edge polytopes. So Alessio is in the audience, so you can ask Alessio about symmetric edge polytopes. And for some simple graphs, there are some explicit formulas for the F numbers and maybe something more. This is just to say, to compute even just the F vector of these polytopes is in general not an easy task, even for an example or a class of examples, except for trees, which is not easy, but at least you know how to do. Otherwise, you have to compute it, will really compute it computationally. So I want to tie up the stratification thing and the phase structure of polytope thing with the last case. So there is something that some literature calls generic metrics. So when is a metric generic? First of all, if the triangle inequality is always strict, and if the polytope is simplicial. This is of course a little bit strange. We don't know the polytope, but I call a metric generic if it is strict and the polytope is simplicial. In our 4-point case, this is exactly the case in the chambers of the arrangement, okay? Basically, generic means you are in the highest dimensional cones of the type fan of these KRW polytopes, okay? So here we know, in this example with 4 points, right, we know that in these 6 regions, we all have this kind of simplicial polytopes, and they really all are isomorphic to each other. Now, if you look really closely and remember, then vertices of these guys, they are labeled, right, by pairs of elements of my metric space. So if you move inside this region, the isomorphism preserves the labels. If you jump over to another chamber, they are still combinatorially isomorphic, but you have to switch the labels. So you have a kind of a strong isomorphism statement, which is the labeled isomorphism, and a weaker isomorphism statement, the unlabeled isomorphism. Okay, so the generic case is kind of neat because turns out Gordon and Petrov prove that if you are a generic metric, they can compute the phase numbers. They don't even depend on the metric. So if you are generic, the polytope, the phase numbers don't depend on the metric. That's, the only other result besides the ones I showed before. And you could conjecture based on this and this that really there is only one combinatorial type for these generic metrics. That's not true. That's actually not true. at least in n equal 5, there are 12 unlabeled combinatorial types of generic metrics. Okay? So here is basically morally my last slide. It's factually my next to last slide, but morally my last slide. So this is done by computation, and these are heavy computations. Of course, I cannot judge this, but Lucas and Leonie can, right? So we kind of enlisted the help of Jörg Rambau in order to compute this. Okay, so Jörg has some new feature in his software which he exploited. So let me just go through this table a little bit with you. So this is the number, right? So on 3 points, nothing really happens, right? The metric cone is not subdivided. There is one hexagon. Okay. So on 4 points, that's the picture we have been looking at, right? So I have 6 label types. That's my 6 chambers, right? And the 6 maximal cones of the Pn fan are exactly the 6 chambers of the arrangement. So here is Pn equal, one is an arrangement, the other one is a fan, but let's, okay. Same thing happens for 5 points. So for 5 points, we have more than one combinatorial types of generic metrics, okay? Again, so that's the case where we have different tight spans that have the same polytope and different polytopes that may have the same tight span. So here again, they coincide, but here you see that they very much not coincide, okay? So here you see where the arrangement is much finer than the type fan of these polytopes, okay? So this is kind of a work in progress, actually. So you can say something about how exactly the arrangement subdivides. Locally, we think we can say something, but there's nothing that they can dare to say in public, even in such a friendly circle. Okay, so that's kind of numerological evidence. Okay, fortunately, we can say, I mean, not even the characteristic polynomial of these arrangements is known. Okay, there is no. Okay, let me do an anagram of the BLT. Now it's the TBL, the bottom line of the end of this. So I have tried to address 3 questions. Okay, so how is the metric cone stratified by combinatorial type of this new kind of polytopes? Is this stratification maybe natural with respect that maybe some nice types of metrics are a union of strata, so it's subfan, right? And of course, what can we say about faces of these polytopes? And the answers, if I may try to condense them. So the answer is polyhedral fan. At least these are polyhedral, right? It's refined by an arrangement. Okay, so but in general, it's coarser. It would be really nice to have a description, or a combinatorial description of the, I don't know, the phase poset of this fan, or I mean, even, as I said, I don't know, characteristic polynomial of this arrangement, just to be able to have some bounds or things, because really above n equals 6, I don't think it is, at least surely not easy to go with brute force computation. So some nice metrics that people have looked at, especially in this biological connection, they are, so the 3 metrics are a subfan, circular split networks are, some are not, and some we don't know. But I don't think this is the right, I just want to mention it. If somebody is interested, the paper is on the archive, by the way. You can look up this. And the phase structure of the polytopes, just give me a metric, what's the phase structure? we know for case of trees, we know in the generic case via Gordon and Petrov, and we know it for the few symmetric edge polytopes that we can give the F numbers. So I kept my promise. This was more about problems than about solutions, but I hope this was at least a little bit interesting, and maybe you are very large number of people, so I hope everybody found at least something to be interested in. And thank you for the attention.
Thank you, Emanuele. Do we have